Good morning, everyone. My name is Tim Lieuwen. I'm at the Georgia Institute of Technology in Atlanta, and thank you very much for the kind invite to present at your meeting. I'm sorry that my travel arrangements didn't allow me to make the trip to be there, but it's good to be with so many former students and collaborators, and look forward to interacting with many of you on these important topics. But I was asked to provide an overview of U.S. gas turbine research and development, but then also just to provide some of my own outlooks and perspectives on R&D needs in gas turbines, particularly around hydrogen and ammonia. And I think really kind of the overarching theme of the work that I'm going to be doing is that just the interplay between gas turbine operability, gas turbine emissions, and gas turbine efficiency, and then also how these interact with a changing fuel mix. So thinking about the U.S. R&D needs, I think it's helpful just to back up for a moment and just think about what the U.S. energy system looks like. And so what I have here is two slides. In this first slide, I'm going to show you what it looks like today, and then a second slide showing what some macro energy analyses suggest that a least cost net zero U.S. economy would look like. And really, if we want to sort of conceptualize the U.S. energy system, or probably any global energy system, we have energy sources, which consist of renewables and nuclear and fossil fuel. And today, fossil fuels are responsible for more than 90% of our primary energy usage. And on the right-hand side, we have our users of energy, which could be automobiles, could be buildings, and today, the largest source of carbon dioxide emissions of the United States comes from our transportation sector. It used to be our electricity sector, using electricity as a means to then do something useful. But today, it's the transportation sector. But the power generation sector, to make electricity, is the second emitter. And basically, the way that the energy system works is that we have these primary energy sources going to steam turbines, gas turbines, nuclear power plants. And about 40% of the final energy delivered to users is in the form of electricity, and 60% in the form of fossil. And this 60% in the form of fossil is largely for our transportation sector and our industrial sector. Now, if we look at sort of what would a net zero CO2 energy system look like? Now, I want to emphasize this is a least cost vision. There's certainly a lot of political constituencies. There's a lot of issues around siting and transmission lines and transitioning of the U.S. workforce and things like that. But if you just said, let me figure out, if I had a goal of getting to net zero, what would be the least cost way to get there? This is what that energy system would look like. And the key difference is the energy sources become dominated by non-dispatchable renewables like wind and solar, but also fossil fuels don't go away. About 25% of energy will be ultimately delivered to users via fossil fuels with carbon capture. The use of electricity as a means of moving energy to the user will grow. But then we'll also have this new sector as well, which will be an enormous sector of renewable fuels. And these renewable fuels will consist of hydrogen, they'll consist of ammonia, they'll consist of liquid fuels like aviation fuels. And the kind of fuel will depend upon the use case, whether it's for electric power generation or aviation or shipping. But bottom line is what you can see here is there's going to be a lot of needs for gas turbines and a lot of needs for gas turbine R&D as we think about how do we build cycles that are efficient, but yet we can capture carbon. And how do we make these cycles that can operate with renewable fuels? And then how do we make these systems that can operate in a much, much more dynamic environment where we have a significant amount of generation sources that are non-renewable, that are non-dispatchable, excuse me. So if I were to summarize kind of an overview of work going on in the United States in R&D, I would really put it in a couple big buckets. I think the first one I would just call cycle innovations. So lots of looking at just different cycles that are optimized for carbon capture. So for example, the alum cycle, which is an oxy-fuel cycle, there continues to be a lot of work and some demonstrations that are going on there. And air breathing systems like conventional gas turbines There continues to be an enormous amount of work in improving the efficiency of these devices, which is being achieved through higher turbine inlet temperatures for combined cycle, which is driving some of the work that I'll talk about both in the turbine and the combustor. But as we go to these higher and higher turbine inlet temperatures, that also, standard combustion approaches for reducing NOx, like lean premixed, run into their limits. And so we're starting to see axially staged systems now, where you're staging the fuel axially in order to achieve low NOx at these elevated temperatures. And then on the combustor side, continues to be quite a bit of work around operability, pollutant emissions, the ability to turn down to operate a power plant at full power, but also at partial power to very rapidly ramp. And that interacts very strongly with this fuel flexibility. So for example, as we start adding hydrogen, or potentially as the amount of hydrogen that you're feeding to a given gas turbine, if it changes, that's a real challenge, right? So it's one thing to design a system to operate statically with pure hydrogen or statically with 50% hydrogen. It's another thing for it to be able to operate one day with pure natural gas, the next day with hydrogen, the next day with a blend, and so forth. And then, as I mentioned, on the turbine, just a lot of work to increase turbine inlet temperatures in life of these systems. So what I wanted to do was just really give the rest of my presentation with two case studies, really talking about these issues, operability, emissions, with respect to hydrogen, and then I'll talk a little bit about ammonia. And the reason for this is that because these are just such a huge driver of R&D needs as we look at this evolving energy mix, both in the United States and globally. And so just a quick reminder about some nomenclature when we talk about combustors is there's really two primary ways. You have a system with a global fuel flow rate, a global air flow rate, but you can mix that fuel and air in different ways. It can be introduced in different ways. You can stage it in different ways. And the way you do that has cost implications. It has operability implications, and it has fuel flexibility implications. And so I'll start with the second one, which would be a non-premixed flame, where you introduce the fuel and the air separately into the combustor. And so where they mix is where they burn. And what happens with this type of flame is it's relatively simple. These types of combustors can turn down easily. You can just turn the fuel flow up and down, but you also lose control of a lot of the details of how the combustion process happens. And it just turns out that these types of flames make a lot of NOx. And if you're burning a hydrocarbon, you also make particulates. Perfectly good approach for oxycycles that don't have nitrogen. And if you're burning, let's say, hydrogen or ammonia, for instance, then those issues go away. But if you're burning a hydrocarbon in air, then you have to worry about NOx and soot with these approaches. Which brings me to the premixed approach, which is where the mixture stoichiometry, the same fuel, same air flow rate globally, but you're going to premix it so you can control the stoichiometry of the flame. And by doing that, you can control, you can have a very big control knob on the temperature at which the reactions are happening, and thereby on the NOx production. What you can also do is you can stage the system. So you could add some of the fuel here, and then you could add some of the fuel downstream. And that's what's being used in for example, the most recent version of very high firing temperature gas turbines produced by manufacturers like General Electric and Siemens. And then finally, you can stage the air. You can put some of the air here, and then you could add some of the air downstream. That's what you might do with an RQL type combustor system. That's what we do in modern aircraft engines today, but that would also be the optimal approach for burning ammonia. Okay, but really I the picture that I want to give to you here is that R&D need, that any given issue around operability or pollutant emissions or turn down, these are solvable issues. The challenge comes with trading them off between each other and then trading off cost and complexity. So I have this little diagram here where I have cost and complexity. Well, if you want a very simple system, a very low cost system, it's going to be difficult for you to get all these other things that you worry about. And as you start having systems with wide operability ranges, so systems that can operate with low power, with high power, that can you can take your power plant pretty much wherever you want it to go. You can ramp it fast, you can ramp it slow. then you're going to start worrying about operability issues like the flame blowing out, or the flame flashing back, or auto-igniting, or combustion instability. These are really some of the three key operability issues that particularly premixed designs, premixed low NOx designs drive. And then pollutant emissions, particularly NOx and CO. And then if you're looking at ammonia, we also worry about things like N2O and even NH3. And so let me just walk through these different issues quickly here. I think there's a number of ways. Let me just back up. The combustor and the R&D interacts very strongly with the fuel. And so let me start with this bottom bullet. Is a lot of the R&D needs today are being driven by fuel flexibility. Because again, as I mentioned in the beginning, it's actually not that challenging, or I'll just say it's not that challenging to design a combustor to operate with pure hydrogen, for instance, as long as it's only pure hydrogen. The challenge comes when you have to design a combustor that can operate with pure hydrogen and with pure natural gas and everywhere in between, just because there's such different flame speeds of those two mixtures. And so the things that you would do for a pure hydrogen system might cause the natural gas flame to blow out. And the design that you would use for pure natural gas would cause the hydrogen flame to flash back. And then if you start adding ammonia, because ammonia has a nitrogen atom that's molecularly bound to the fuel, the strategy that you use to minimize NOx is fundamentally different than if your fuel is hydrogen or methane. It doesn't contain a nitrogen atom. And so NOx then comes from the nitrogen in the air, N2 in the air. And if you're burning a hydrogen or methane and your NOx is coming from N2 in the air, the nitrogen atom in the air has a triple bond. It's very strong. So as long as you keep your flame temperatures low, those N2s are going to stay N2. They're not going to dissociate into N atoms. As soon as they start dissociating into N atoms, those nitrogen atoms very quickly react with oxygen to form NOx. And so the key strategy is the lean premix strategy. Whereas, as I'll mention a little bit later with ammonia, just by the very act of ammonia reacting, you have nitrogen atoms out there. And so if you use a lean premix strategy, you will actually make a lot of NOx, and a lot of the sensitivities to temperature and things like that are quite different with ammonia. But let's walk through down this list and let's talk a little bit about each one of these: operability, pollutant emissions with respect to fuel flexibility. So starting by blow off, so the word means just what it says. It's where the flame blows out of the combustor. So this is an SR-71, and you can see the flame is not in the airplane. So this is an example of blow off, and this is a real challenge. It happens when the flame just simply leaves the combustor, and this happens because you have very, very high velocity flows. For those doing combustion R&D, though, I want to also mention that you can have what I might call global blow off, where the flame blows out of the system completely. But you can also have where the flame simply, what I'll call locally blows off. For example, this is a very common geometry, what I have here on the right, where you have an annular gaseous flow with the center body. The flow would be swirling. You're going to have a low velocity shear layer, this inner shear layer. You'll have a low velocity shear layer, this outer shear layer. So if the flame can attach in both spots, you're going to get a picture that looks like this. Whereas as you start dropping equivalence ratio or dropping ambient temperature, or maybe diluting the fuel with diluents or increasing the flow velocity, what can happen is the flame can locally blow off. So if it can no longer stabilize in the outer shear layer, it might look like this. Or if it can no longer stabilize in the inner shear layer, it might look like that. Or if it can't sit in either shear layer, but it's stabilized by the vortex breakdown bubble associated with the swirling flow, it might look like this. As you can see, these are four fundamentally different flame shapes controlled by where the flame can and cannot sit. Fuel composition has a significant influence on where these flames will bifurcate between these different shapes. And these all have different influences on things like what you need to design for high temperatures. As you can imagine, this type of geometry isn't going to be pumping any heat into this hardware, whereas this geometry right here might turn this whole bulkhead up front glowing red. The length of the flame changes too, which directly controls combustion instability. But bottom line is, as you add hydrogen, you significantly extend blowout. This is some data just showing the equivalence ratio of blowout versus percent hydrogen. And this equivalence ratio drops by about a factor of 2. And so the range of mixtures that you can operate, particularly as you go to lower power, lower equivalence ratio, goes up as you add hydrogen. And that's just due to the fact that hydrogen has a very, very fast flame speed. Okay, well, that's blowout. Now let's talk about flashback and autoignition. Now, flashback and autoignition are different physical phenomenon, but they manifest themselves in the same way. So if we go back to this sketch, when we premix fuel and air, we create the possibility for, we have a combustible mixture here. The flame can either propagate upstream through flame propagation, that's flashback, or the mixture can autoignite on itself. It can just ignite, that's autoignition. And flashback is upstream propagation of a premixed flame into a region not designed for the flame to exist. It occurs because, as you can see here, this is data from Eric Peterson, flame speeds, pure, a very high hydrogen mixture here, pure methane here, and you can see there's about a factor of 4 increase in this data in the flame speed. And so flames, it's just much harder to keep the flame from propagating upstream, particularly in these low velocity boundary layers. And then on the other hand, autoignition. This plot right here shows if you take a mixture and you premix it, how long will it take that premixed mixture to just spontaneously ignite? We call that the autoignition delay time. Here it is in milliseconds, and you can see this is a log scale. It varies by an enormous range. And it varies by an enormous range because it's so temperature sensitive. So this plot here is the inverse of the temperature. It's 1,000 divided by temperature. So as we go to the left, temperature is increasing. And again, you can see pure methane is this black line. The very high hydrogen blend is this line right here. And the high hydrogen blends will ignite much, much faster. So again, the hydrogen system, it's much harder to keep this hardware that's upstream from being damaged by the flame. And then lastly, we have the issue of combustion instability. In combustion instability, it refers to large amplitude acoustic oscillations that are driven by heat release oscillations. They occur at specific frequencies, they're associated with resonant combustor modes, and they're very sensitive to fuel composition. Just a simple plot, just to illustrate this, is that this is just a notional plot showing combustion instability amplitude as a function of this dimensionless parameter, what I've called tau convect times F. F is the natural frequency of your combustor, so it'll be a function of how long your combustor is, for instance. And tau convect is basically a ratio of the flame length divided by the flow velocity. So anything that changes the flame length is going to move you around in this space. And so, for example, if your combustor, let's say, is you design it to be to sit right here where the amplitude is nearly 0, and let's say that's condition 1, but if you do something to make the flame shorter, condition 2, it will become unstable. So this would be an example where maybe the addition of hydrogen could make a stable system very unstable because you're making the flame shorter. Whereas if, let's say, your notional design for natural gas was here, where it was unstable, the addition of hydrogen would make the system stable. So I think my key point here is that you can't really make definitive comments on whether combustion instabilities will be better or worse with hydrogen. What hydrogen will do is it will move around where combustion instabilities occur. The one exception to that is combustion instabilities that occur under very close to lean blowout conditions. And because hydrogen makes it harder to blow out, it will make those stable. Okay, let me say a few things about pollutant emissions now. And there's a lot of different pollutants we worry about. NOx, which comes from carbon monoxide, soot and particulates, SOx, if there's sulfur in your fuel, the CO and soot. These are pollutants that come when you have from hydrocarbons. When you have carbon atoms in your fuel, rather than being converted into CO2, they're not completely oxidized in terms of CO, or you get carbonaceous particles like soot. And then you have NOx. NOx, as I mentioned before, can come either if you have nitrogen in the fuel, that's similar to what I said about the SOx, or it can come from just ambient nitrogen in the air. And so a key point that I want to make, particularly about nitrogen, NOx emissions, is that a 100% renewable technology that emits 0 net CO2 can still make NOx. Because anything that you do to heat up air, where air is composed of N2 and O2, can lead to NO production. Let me back up. I'm not going to say it will lead, because this is where combustion R&D is necessary. And when you add hydrogen, what you do is you change NOx production pathways, you change sensitivity of systems to mixedness. And so remember, these systems are nominally lean premix systems. You want to premix to get low NOx, whether you're burning hydrogen or natural gas. But you're going to have you're always going to make trade-offs. It's not going to be perfectly premixed. And so the sensitivity to premixedness, and then sensitivity to things like turbulence. And so here I just have a plot. This is actually for natural gas, plotting how NO emissions change with the residence time, essentially the length of the combustor. And you can see NO emissions increase monotonically the longer you make your combustor, and they also increase exponentially with temperature. And which is why, as we go to higher efficiency machines, NO wants to go up because turbine inlet temperatures are going up, and so that requires different types of more advanced fuel staging schemes. But now, if we think about at a constant temperature, what the sensitivity of NOx is to hydrogen addition, it appears that in the premixed limit, there is actually not much sensitivity. So this is actually good news. And so I want to emphasize there's a lot of data in the literature which you should just ignore. It's not good data. People aren't, as they're adding hydrogen, they're making NOx measurements, but they're not necessarily controlling, because when you add hydrogen, you're going to change something. So what are you keeping constant as you're comparing how hydrogen addition does things? And so I think really the proper parameter to keep constant, particularly for the gas turbine application, when you want to think about NOx sensitivity of hydrogen addition, is at constant temperature. So if I were to run two flames with the same temperature, different hydrogen methane ratios, what happens? So that's what this plot is showing you. This is some calculations from our group. Fuel composition, so 0 would be pure natural gas, 100% would be pure hydrogen, and the y-axis is just two measures of NOx. One is nanograms per joule of NO, the other is ppm. And then I have sort of two different combustor designs. This asterisk one would be a 5 millisecond combustor design, like an aeroderivative. The 15 millisecond combustor design would be like an industrial or frame gas turbine. And what you can see is these plots are pretty flat. In other words, there's a little bit of fuel sensitivity, but by and large, adding hydrogen, as long as you're premixing, should not increase NOx production from blending it. Okay, so let me just say a couple things about ammonia. Now, everything I just said earlier about ammonia about hydrogen applies. Just the difference is ammonia is, whereas hydrogen propagates really fast relative to natural gas, ammonia propagates really slow. And so flame stability and blowout becomes a much more significant issue. And then the other key difference from hydrogen is that you have this molecularly bound nitrogen atom. And so you need a different combustion strategy to reduce NOx. If you run ammonia in a premix system, a system that would be optimized for low NOx production with any kind of hydrocarbon fuel or hydrogen fuel, you will make enormous amounts of NOx burning ammonia. 1 or 2 orders of magnitude more, thousands of parts per million of NOx. And so really what you want to do is you want to run what's called an RQL system. These are very mature, well-developed combustion systems for aircraft engines. For aircraft, they're used for systems that have to have very high turn down. That, an aircraft engine has to take off, it has to idle and operate everywhere in between. But in essence, what you do is you stage the air. So you put part of the air on the front, and so you're running rich. And the reason you want to do that with ammonia is that you actually don't form NOx really when or equilibrium, at least NOx levels want to go towards very, very low levels if you're burning rich. And so you burn it rich. The products of rich combustion of ammonia is basically hydrogen and nitrogen. And then in essence, what you have then is a system where you have to burn hydrogen and nitrogen in the second lean stage. And a useful benchmark, though, is theoretical minimum. What if we could make these RQL systems work perfectly? How low could your NO levels go? How low could your N2O levels go? And we've been actually doing some calculations like that here at Georgia Tech. And I just want to show you, and we will actually be presenting these results at the Turbo Expo. And this just shows minimum NOx levels, nanograms per joule on the y-axis, ppm on the x-axis as a function of pressure. And you can ignore, just the main thing to look at is this green line. And you can see that by operating at high pressures, let's say at this 20 bar condition, you can actually theoretically approach sub 25 ppm NO levels. That's at 1750 K combustor exit. You can see here, this is at 1900 K. There's actually not much sensitivity to exit temperature. And again, that's a difference between ammonia combustion and where you're making your NOx from the nitrogen in the air, which is very sensitive to combustion. And in fact, you can get even lower levels if you go to higher pressures or you design combustors with longer residence times. And so in this case, this calculation was with a 20 millisecond combustor residence time, which would be typical of a current combustion system. But if you could do a retrofit where you had a longer residence time, you could get even lower. So with that, I'm going to conclude just to summarize lots of really interesting challenges as we look towards a system with renewable fuels. What the optimum combustors look like will be very different for a hydrogen type economy versus an ammonia economy. Again, we can design combustors that can address operability and fuel flexibility and turn down for hydrogen, for natural gas, for ammonia. Just key challenges come as we start to vary these fuel compositions, and the same combustion system has to do all of them. All right, well, I'll look forward to the conversation time with all of you, and thank you again for it.
네, 루엔 교수님께도 저희가 온라인으로 받은 질의를 드리도록 하겠습니다. GE나 지멘스, 또 MHPS와 같은 주요 지상 기반 가스터빈 기업들은 최근 기존 가스터빈을 개조하여 100메가와트 이상급의 대형 가스터빈용 수소의 최대 50%까지 수소 동시 연소를 구현했습니다. 이들 기업들이 진정으로 수소나 암모니아와 같은 무탄소 연료를 100% 사용하여 말 그대로 탄소 중립적인 대형 가스터빈을 개발하고 있거나 계획 중일까요? 만약 그렇다면 어떤 장애가 예상되며 본격적인 적용은 언제 가능할 것으로 보십니까?
All right, so I want to address this question, which is, this is a question regarding gas turbine development using carbon-free fuels. Major land-based gas turbine companies like GE, Siemens, and MHPS have recently retrofitted existing gas turbines to demonstrate hydrogen co-firing up to more than 50% of hydrogen for large-scale gas turbines. I'm wondering whether these companies are developing or plan to develop literally carbon-neutral large-scale gas turbines using 100% of carbon-free fuels like hydrogen or ammonia. And if so, what is the current state of the development, including major obstacles expected, and when do you think it will be possible for full-scale demonstration? Okay, so I want to break this question up into two pieces because the issues around hydrogen combustion and the issues around ammonia combustion are different. And the reason for that is because if you're worried about NOx emissions, so if you're if you have a customer that has regulations on NOx emissions, the NOx emissions implications are substantially different when you burn hydrogen. And when you burn hydrogen, the NOx will come from the atmospheric nitrogens and oxygens in the air reacting. And so you're going to want to use conventional lean premix strategies to do that, like we do today with natural gas. In converse, if you're burning ammonia, because ammonia has a nitrogen atom in the fuel, that as the reaction proceeds, you will have N atoms floating around. Those are going to react. And if you burn in a lean premix mode, you will make thousands potentially of parts per million of NOx, even in a perfectly premixed system. And so ammonia combustors, either you'd have the decision to, if you were going to run a diffusion flame or a lean premix system, like you would in a conventional gas turbine for burning, even a liquid fuel, hydrogen or natural gas, you're going to make a lot of NOx, and you're going to have to either have a very large gas cleanup or completely put in a fundamentally different types of combustion systems, essentially an RQL, a modified RQL type combustion system to optimize NOx. So let's talk about hydrogen specifically. So what is the key technology challenge associated with low NOx hydrogen combustion? Well, again, to do low NOx hydrogen, you want to run lean and premixed, and so immediately you are dealing with operational challenges like I talked about in my presentation. And these in particular are flashback, is that hydrogen is very flashback prone, particularly as you go up in pressure, it gets very, very difficult. But you can design around that. The challenge comes if you want to use the same set of hardware that can burn a variable blend of hydrogen and natural gas. So if you have to use the same technology to burn pure methane or pure hydrogen, that's kind of where the current state of the art in technology is that technology doesn't exist. And so what you see happening with the OEMs is all of these major OEMs have a certain set of hydrogen capacity that they can run their lean premix systems in. You know, initially, let's say it was 5% hydrogen, it's getting increased to 20%, now even 30% hydrogen. But remember, that's usually hydrogen by volume. If you calculate the amount of actual energy that's released via hydrogen, you know, 20% hydrogen by volume is only about 7.5% of the energy comes from hydrogen. You know, if you want half the energy to come from hydrogen and half to come from natural gas, you actually have to have 75-25 blend. So in other words, 75% of the fuel would be hydrogen. And so really where the technology is in terms of these major OEMs is developing technologies that can take natural gas, but have more where you can push up the max blend of hydrogen. It's possible. And in fact, I think all of these OEMs have done it, at least in their own labs, running 100% hydrogen. Again, just the challenge comes is that's 100% hydrogen technologies, you know, being able to also operate them reliably with natural gas. So hopefully that addresses that question. Thank you.
네, 교수님 감사합니다. 큰 박수 부탁드립니다.